Hello class. We're starting chapter 9, the gas laws. So today we're going to go over sections 1 and 2. Hot air inside these balloons is less dense than the surrounding cool air. This results in a buoyant force that causes the balloons to rise when their guy lines are untied. Section 9.1. Gas pressure. Define the property of pressure. Define and convert among the units of pressure measurements. Describe the operation of common tools for measuring gas pressure. Calculate pressure from manometer data. Air has been known to exist since ancient times. I believe all of evolution has occurred in the air. The Greeks considered air one of the four fundamental elements of nature, along with earth, water, and fire. Actually, if you take a straw and you stick it in a drink and you cover one end with your thumb so that no gas passes, and you can pull it up, the liquid remains in the straw. This is an evidence that you've got this substance of air, that your thumb has to be removed to let that substance in one end so that the liquid can fall out of the straw. So that's how they knew that air had a substance to it. The 14th century Lavoisier, Cavendish, and Priestley determined that air is actually a mixture of gases. Lavoisier and Priestley were credited with discovering oxygen. Air in the news. The atmosphere has some issues. One in the 1980s was the depletion of ozone in the stratosphere from the freons used for making styrofoam and making refrigerators, as well as aerosol cans. Laws came into place that got rid of those things, and we think we've got the ozone depletion in the stratosphere under control. We think the stratosphere is actually healing. The next problem is carbon dioxide, and carbon dioxide continues to grow and contribute to global warming, and that is a longer term and more difficult problem to solve because it's intrinsically linked to our sources of energy. Okay, the atmosphere is very deep. If you were to take a 1 square inch column and take it all the way to the edge of the atmosphere, its weight would be 14.7 pounds. However, pressure doesn't exert itself vertically like it was a column of solid material or a column of water, but it exerts that pressure on all surfaces, the bottom surface as well as the top surface, which is why we don't notice the pressure of air that much. So the atmosphere above us exerts a large pressure on objects at the surface of the earth, roughly equal to the weight of a bowling ball pressing on an area the size of a human thumbnail. Remember this number, 14.7 pounds per square inch. This is a value of pressure known as 1 atmosphere. It is the pressure of the atmosphere at sea level on the average. Pressure is defined as the force exerted on a given area. Gas pressure is a result of the forces exerted by gas molecules colliding with the surface of objects. The English system for pressure is pounds per square inch, or PSI. A mercury barometer is a device used to measure the atmospheric pressure. Barometers measure the atmospheric pressure, and low pressure usually signals bad weather. So a barometer can predict the weather in a sense. As it gets lower, you expect the weather to get worse. Although an elephant's weight is large, creating a very large force on the ground, the figure skater exerts a much higher pressure on the ice due to the small surface area of her skates. So, a lot of weight, a lot of surface area, a lot less weight, but a lot smaller surface area, and this actually generates more pressure on the ice than this does on the grass. Due to the way gas pressure is measured, millimeters of mercury is a commonly used unit of pressure. A column of mercury stands about 1 foot high, about I'm sorry, it's more than a foot. It's 29 centimeters high. Wait a second. Scratch all that. And it's 29 inches of mercury, which is 760 millimeters of mercury. mmHg is a commonly used unit of pressure. Water can only form a column that's about 30 feet tall, and mercury is about 15 times as dense as water, so it forms a column that's about 1/15th that of the height of water. You can only suck water up 30 feet before it forms a gap of vacuum and cannot be sucked up any further. We don't experience that in our daily lives because we don't usually suck water up 30 feet. But if you have a pump that you're trying to pump out of a well, you will not be able to pump that water up higher than 30 feet. And that's all because of the pressure, the atmospheric pressure supporting that column of water or that column of mercury. If the atmospheric pressure were higher, you would be able to pump water higher than 30 feet. Probably the most common unit of gas pressure is the atmosphere. And an atmosphere is normal atmospheric pressure, that is the average atmospheric pressure at sea level, and it is 760 millimeters of mercury in height. It's also, one atmosphere is 14.7 pounds per square inch. Those are equivalent measures of one atmosphere. The SI unit for pressure is the Pascal. 1 Pascal is defined as the pressure exerted by a 0.1 millimeter high film of water on the surface beneath it. We also have kilopascals because this is so small. We would like to consider 1,000 times this, or 0.1 meters, 10 centimeter high film of water. A related unit to pressure is the bar. A bar is, that's an exponent here. 10 to the 5th pascals. 100,000 pascals is 1 bar. The funny thing about a bar is almost 1 atmosphere. 1.013 bars is equal to 1 atmosphere. So it's only off by 1.3%. It's 1.3% less than an atmosphere. And 1 atmosphere is 760 millimeters of mercury. There's the term torr after the Italian physicist Torricelli. So they named the millimeter of mercury after Dr. Torricelli. And then you've got the pounds per square inch, or PSI, and put into pascals, that 1.013 is actually 100 and 1.3 kilopascals. Say 1 bar is 100 kilopascals up here. That is 10 squared times 10 to the third. 10 squared being the 100, 10 to the third being kilopascal. The barometer measures pressure in terms of the height of a column of liquid of mercury. The atmosphere exerts a force on the liquid mercury, causing it to rise. What's in the top, what exists above the column, is a vacuum. Essentially, the way you make a column of mercury is you take a very long test tube and you fill it with mercury, and then you stick the whole thing into a bowl of mercury, and then raise the column so that the surface remains under the liquid. But the sheer weight of the mercury will pull a vacuum in the top of the test tube. I should say in that closed off bottom of the test tube that's sticking up now. It will cause a gap of a vacuum. And as the atmospheric pressure outside changes, how much vacuum exists in that tube is going to change. It adjusts the height of the column of mercury based on the pressure pressing on the bowl, the open surface in the bowl of mercury. The atmosphere exerts a force on the liquid mercury, causing it to rise. Commonly, the pressure of the atmosphere at sea level pushes the column of mercury to approximately 760 millimeters high. Okay, so here's your bowl of mercury. This is your test tube that's inverted. As they point out, it has a vacuum here. Now, this can be done with water too, but water goes up 33.9 feet before it pulls a vacuum. That because mercury is 15 times more dense than water, it's 1/15 the height, that is 760 millimeters, at which the vacuum is pulled in trying to suck mercury above its liquid level. In a barometer, the height of the column of liquid is used as a measurement of the air pressure. Using very dense liquid mercury, left, permits the construction of reasonably sized barometers, whereas using water, right, would require a barometer more than 30 feet tall. Pressure varies with the height of the column of air above. Okay, so it's saying that the reason why our pressure here at the surface varies is that the air above us changes height, is what it's saying. I'm sure it gets rarefied. It probably takes on it's hard to say exactly what the height of the atmosphere is, because it gets continually more rarefied as you continue out into outer space. But you understand what they're trying to say is that there's less air above us. That's when we have less pressure here at the surface. We don't notice atmospheric pressure, but we do notice changes in atmospheric pressure. And you can notice that when you're descending in a plane that your ears need to clear. You need to yawn to open your eustachian tube to take the pressure out of your ears. So we do notice atmospheric pressure changes. The force of the gas in a flask is measured relative to the force of the atmospheric pressure. So if we have a bottle that we close off and it gets more and more pressure to it, the force on the flask is the difference between the pressure inside the flask and the atmospheric pressure outside. So if you took all the air from inside of a flask, then the atmospheric pressure would crush it. If it matches the pressure of the atmosphere outside, then it will have no stresses on the walls of the flask at all. The distance and relation that the mercury travels is related to the pressure of the gas. Okay, it's just saying that the higher the pressure on the bowl of mercury, the higher the mercury column is. Okay, a manometer can be used to measure the pressure of a gas. A manometer is just like a barometer, except that this is a barometer right here. This is like the open side of the bowl. And so as this sees higher and higher pressure, it increases the height of the liquid, and what's on the other side is a vacuum. Now we can open this end to the atmosphere, and now we can talk about the the difference in pressure from the atmosphere to this piece of gas right here is entirely due to this height and its the density of the liquid. I have my doubts about this. We'll have to get back to that and think about it. But in this case, this pressure is less than atmospheric pressure because this column of water is pulling on that gas. In this case, this column of water is pushing down here and pushing on this, and so this is a higher pressure than the atmosphere out here. I see what they're saying here. This is the pressure of the gas is absolute, depending on the height of this liquid versus a vacuum. In this case, it's the difference between the outside pressure and the pressure in the tube pulling on this gas right here. In this case, this pressure is higher than atmospheric pressure is pushing on it. A manometer can be used to measure the pressure of a gas. The difference in height between the liquids is a measure of the pressure. Mercury is usually used because of its large density. Just a little thing is that water is often used in a manometer for very small pressures, like measuring, pointing a tube into the wind in order to measure the speed of the wind. And so it's not always mercury that's used in a manometer. So this is, again, just reproduction of the figures here. And it comes from examples in the text. A medical technician prepares a patient's blood pressure with a sphygmometer. A typical sphygmometer uses a valved rubber bulb to inflate the cuff and a diaphragm gauge to measure pressure. I've got a battery-operated sphygmometer to use on my wrist. Meteorologists use weather maps to describe and predict weather. Regions of high and low pressure have large effects on weather conditions. The gray lines represent locations of constant pressure known as isobars. These lines right here. The Earth's atmosphere has 5 layers: the troposphere, the stratosphere, the mesosphere, the thermosphere, and the exosphere. The exosphere is also known as outer space. We live in the troposphere, and it says it goes up to 12 kilometers. And so all the mountains and everything that we experience on the surface of the Earth, including the tip of Mount Everest, occurs within the troposphere. The stratosphere is higher than that. That's where most airplanes fly, higher than Mount Everest. And then you get into the more complicated phenomena, mesosphere and thermosphere, where the air is extremely thin, so much so that we would hardly call it the atmosphere if we were to try to breathe it. Okay, that was section 9.1 about pressure. This relates pressure, volume, amount, temperature, the ideal gas law. Identify the mathematical relations between the various properties of gases. Use the ideal gas law and related gas laws to compute the values of various gas properties under specific conditions. At constant temperature and pressure, a gas expands uniformly to fill the container in which it is contained. There are many different types of gases. There are the elements: argon, helium, hydrogen, which is in the diatomic form, nitrogen, dinitrogen, dioxygen. There are compounds: CO2, CO, carbon monoxide, H2O. It's frequently a gas. It's a gas around us at low pressure, as well as a liquid. And ammonia. All gases have the same dependence on these 4 properties: volume, amount, temperature, and pressure. I think they're stretching it a bit to say the same dependence. It turns out that at low pressures, all gases behave the same. At higher pressures, there are deviations, and chemical engineers know how to account for that. In 1783, the first hydrogen-filled balloon flight, B, manned hot air balloon flight, and C, manned hot air balloon flight occurred. Okay, so that's hydrogen-filled, manned, and manned hot air, and manned hydrogen-filled. When the hydrogen-filled balloon depicted in A landed, the frightened villagers of Gonis reportedly destroyed it with pitchforks and knives. The launch of the latter was reportedly viewed by 400,000 people in Paris. So that looks like the destruction. And this looks like the launch was, and these are 400,000 people down there. Okay. The effect of temperature on gas pressure. When the hot plate is off, the pressure of the gas in the sphere is relatively low. So this is it, and this is the pressure. As the gas is heated, the pressure of the gas in the sphere increases. So this is medium, has medium pressure. On high, this is high pressure. So the pressure goes up with temperature. The pressure of a gas is inversely proportional. the pressure of a gas is directly proportional to its temperature in Kelvin. Okay, now this is important because we've got three temperature scales, Celsius, Fahrenheit, and Kelvin. The only temperature that is ever going to count in the gas law is Kelvin. So in order to double the volume of a gas, let's say a gas is at 273 Kelvin, which is the freezing point of water, 0 Celsius, it would have volume A. To double that gas, to double that gas pressure, you'd have to double the temperature in K. So if it's 273, then you'll have to go up another 273 degrees. 273 degrees Celsius, or what would that be? That would be 546 degrees Kelvin before you doubled the pressure on that gas. So they've chosen to use a K here. It should have been an R for all they're trying to say is that this is a constant. So P is proportional to T. It's unfortunate that their proportionality constant was chosen as a K when we're talking about temperature in K, in Kelvin degrees. Anyway, this is the Gay-Lussac's law, or Amundsen's law. Okay, for a constant volume and amount of air, the pressure and temperatures are directly proportional, provided the temperature is in Kelvin. Measurements cannot be made at lower temperatures because of the condensation of the gas. That's the reason why this is a dotted line. You can think of this pressure as going boop, 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 and then boom, hitting the ground at this point. When this line is extrapolated to lower pressures, it reaches a pressure of 0 at minus 273 C, which is 0 on the Kelvin scale, and the lowest possible temperature called absolute 0. The volume of a gas is directly proportional to its temperature in K. By the way, this lowercase k just simply means it's a constant, and it's not the same as what was in the previous slides. So all they're trying to say here is proportional to. So volume is proportional to temperature. So, and that's holding pressure and the number of moles of gas constant. So the volume of a gas is directly proportional to its temperature in K at constant pressure and number of moles. This is Charles's law. So again, it's the same thing. Its volume will go to 0 when the temperature goes, the absolute temperature goes to 0 degrees Kelvin. The volume and temperature are linearly related for 1 mole of methane gas at a constant pressure of 1 atmosphere. If the pressure is in Kelvin, volume and temperature are directly proportional. The line stops at 111 Kelvin because methane liquefies at this temperature. So you can think of the volume as going boop down to a very small value here. When extrapolated, it intersects the graph's origin, representing a temperature of absolute 0. When a gas occupies a smaller volume, it exerts a higher pressure. When it occupies a larger volume, it exerts a lower pressure, assuming that the amount of gas and the temperature do not change. By amount of gas, meaning moles of atoms, which we call lowercase n. Since P, pressure, and V, volume, are inversely proportional, a graph of 1 over P versus V is linear. So this is 1 over P versus V, the volume, is linear. This is P, the pressure. This is the volume. You see it has this curve, but we can show that it follows, that P is inversely proportional to V by plotting it this way, and we get a straight line. The volume of a gas is inversely proportional to its pressure at constant temperature and N, which is amount or number of moles. So again, this K is not the same K as in the other slides. It's simply a way of saying is proportional to. So volume is proportional to 1 over the pressure. This is Boyle's law. A relationship between pressure and volume is inversely proportional. The graph of P versus V is it's not that. They got a mistake there. That's not a parabola. That's a hyperbola. Whereas B, the graph of 1 over P versus V is linear. Breathing occurs because expanding and contracting lungs create small pressure differences between your lungs and the surroundings, causing air to be drawn into and forced out of your lungs. The volume of a gas is directly proportional to its amount, that is moles, at constant T and P, at constant temperature and pressure. So V is equal to, again, this K is not the same K as all the other things. They're simply saying is proportional to N, the number of moles. This is Avogadro's law. And this is what Avogadro was known for. He never knew the value of Avogadro's number. So all these laws are squeezed together into what we call the ideal gas law. And that's the product of the pressure times the volume is equal to the number of moles times the temperature times a constant called R. Now this one is a single constant that has a value. This is the ideal gas constant. So let's see what the slide says is that these 4 equations can be combined into a single law consisting of all 4 properties. The 4 constants, K, were combined into a new constant, R, called the ideal gas constant. When pressures in atmospheres, which is pretty much all we're going to do, we're going to convert from millimeters of mercury to atmospheres, and we're going to convert from psi to atmospheres, but we work with everything in atmospheres. V is in the volume in liters. Again, if we have milliliters or gallons, we're going to convert them into liters. N is the moles of the gas. T is the temperature in K. We don't use Celsius and we don't use Fahrenheit. And R is the ideal gas constant. R equals 0.02806 liter atmospheres divided by moles Kelvin. The ideal gas law accurately describes the property of an ideal gas. What is an ideal gas? What assumptions are being made? Well, I'll tell you one is it's low pressure, but our atmosphere is very low pressure with respect to most of the gases that we deal with. So pretty much the ideal gas law is very applicable to almost anything we do with gases at 1 atmosphere. Scuba divers use compressed air to breathe while underwater. Now, the ideal gas law would have to be modified a little bit for very high pressures used in the scuba tank. I think they've got I'm not exactly sure what the highest pressures they use, 20,000 psi, something along those lines. Scuba divers, whether at the Great Barrier Reef in the Caribbean or in the Caribbean must be aware of buoyancy, pressure equalization, and the amount of time they spend underwater to avoid the risks associated with pressurized gases in the body. That's an aside that nitrogen dissolves in our blood at high pressures, and if we don't observe strict rules for resurfacing, we resurface too quick. The gases, nitrogen in particular, will boil out of our blood, causing a disease called the bends. Sometimes it's important to define standard conditions. Standard temperature and pressure. Okay, it looks like this text is going to have 0 degrees C as the standard temperature and 1 atmosphere as the pressure for working with the ideal gas law. It says here that in 1982, IUPAC recommended the change from atmospheres to 1 bar. And I've seen that in the thermodynamic tables. Also, a lot of cases, we're going to be in the thermodynamics soon, and oftentimes the standard temperature for thermodynamics is 25 degrees C. But this is STP as we're using it for the gas law. 0 C, 1 atmosphere. Regardless of its chemical activity, 1 mole of gas, behaving ideally, occupies a volume of 22.4 liters at standard temperature and pressure. So it doesn't matter if it's helium, 4 grams, 1 mole of helium, or 1 mole of ammonia, or 1 mole of oxygen. They all occupy the same volume of gas. And that's it for today. Thank you for listening.